Hello, my name is Devendra Kapadia, and this afternoon my colleague Adam Strzebonski and I will give a talk on Limits Unlimited, where we'll describe the new and exciting functionality for limits in version 11.2. We'll talk about various kinds of limits and also show a comparison with literally 1 million examples with some other software to show how powerful version 11.2 is for limit computations.
So, changes in function limits. So first, we extended univariate limit scope. So univariate limit has been here since version 1.0, but we have improved it in 11.2. We introduced undirected limits. So setting direction goes to reals gives limit from both directions, both real directions, and direction goes to complexes requires limit from all directions in the complex plane to exist. Limit can now return conditional results. It will return indeterminate if it proves that no limit exists, so this is new. And we introduced multivariate limits. Now that's something that was not here at all, and mean limit and max limit, otherwise known as limit inferior and limit superior. And there is a whole new documentation for limits, much more examples, and a new typesetting, which I'll show throughout the talk. So, first, is this large enough? Should I make it? Yeah. Okay, so major extension of the univariate limit is we added new implementation of Grun's algorithm. There was implementation of Grun's algorithm, but it was limited to X-block functions, so only compositions of exponentials logarithms. Now it also can be used for other real functions. So here's the first example, the limit that we could not compute in the previous version. Now we can. Here's something slightly more complicated. Here it is. And so we used the benchmark of 1 million limit collected from Wolfram alpha, and we improved success rate from 93% to 97%, or in other words, failure rate is more than twice lower than it was. That sounds better. So first, undirected limits. So earlier versions of limits were computed directed limits. So if you just say limit, the direction would be from the larger values, larger real values. So what's now you can say direction from above, and it typesets nicely as x goes to 0 plus, like the natural mathematical notation, and for 1 over x, from the right-hand side, the limit exists and is plus infinity. But if we take the limit over the reals, which is the new default, it doesn't exist. From the right-hand side, it's plus infinity. From the left-hand side, it's minus infinity, so the limit does not exist. So to get the old behavior, one can use direction goes to -1 or from above to get the same behavior. Now, direction goes to complexes requires the limit to exist from all directions in a complex plane. So here we have a function where the limit from both real sides exists. It's 0, but the limit over the complexes does not exist. And we can check that if we take direction from positive, actually this one is from negative complex axis, then we get plus infinity. Okay, conditional results. So now limit can return conditionally valid results. So the old limit would fail if it required some non-generic conditions on parameters, and the new limit will introduce some condition and give you a conditional expression output. Like here, if n is greater than 0, then the limit is infinity. And the conditions are chosen to be consistent with assumptions. So the same example, but now we say that n has to be less than 0, and it came up with value for n less than -1. So it's consistent with the, and the value is 0, so it's different. And if we say generate condition goes to none, so if you don't want to get conditional results, you can say generate condition goes to none, and it will not go into the code that generates the condition. And there is one more setting, generate condition goes to false, which, well, the conditions are generated but not reported. Not, if you really don't want to get conditional expression as the output, just want limit that's valid somewhere, that's the setting. Okay, another difference with the older version. So right now, if we take the limit does not exist, we get indeterminate. So that means that we have proven that the limit does not exist. So that's considered better than returning interval. Interval is returned if we cannot prove that the limit does not exist, but we have bounds on the set of limit points. So like in this case, this is like too difficult for us right now to prove that the limit does not exist here, but we can easily bound the set of limit points, and it's interval -2 to 2. The older versions of Mathematica were always returning intervals in such cases when it could compute intervals. So for sine, we would get the interval -1, 1, and if somebody prefers to get bound on the explicit bounds on the set of limit points, then there is a method allow indeterminate output goes to false. With that, we will always get interval if we can get it. So now multivariate limits. So in the new version of Mathematica, we have multivariate limits. So it's limit as x and y go to 0. So it's limit in 2 dimensions, and here we can compute for rational functions. We can always compute it. You can see the plot. The function actually is continuous here. It has a limit. Here is a different rational function, and it does not have a limit. We can see it on the plot. So if we rotate it slightly, you can see that the limit can be, we have whole interval of limit points at 0. Okay, so that here, this shows that the limit is computed over the set of points where the function is defined. So we have a function where the denominator is 0 if x is equal to y. So on the cross, the function does not exist, but everywhere else where the function is defined, the limit exists. So the limit will report the limit exists and is equal to -2 at 0. Here we have a function with 3 variables. We can prove that it doesn't have a limit. So a complete algorithm exists for limits of rational functions, but we have many special case methods for other cases, so for more general functions. And the success, so again, we have a benchmark extracted from Wolfram Alpha, 120,000 multivariate limits, and the success rate was 91%. Min and max limit, so we can compute limit inferior and limit superior of functions. For instance, for this combination of trig functions, the limit inferior is this number, and limit superior is another. Oh, I will show it on the plot. These are numbers, real numbers. And here they are the lines correspond to the computed numbers. So the wiggly function stays between those numbers. No, it will tell you indeterminate. So in this, unless you set the option that makes interval preferable to indeterminate. So the preferable is indeterminate because it says that we have proven that the limit does not exist. Interval, the limit may still exist. Might. Right. In this particular case, you probably will get the tight interval because it's the same method that computes min limit and max limit. So, but in general, it's no guarantee. Right. So the really safe way to get tight limits is to use min limit and max limit. Yeah, so this is the same example. We can so we can plot the bounds so we can see that the function is between the bounds, min and max limit. Here's another function. So that's the case of trig functions with not commensurate periods, or periodic functions with not commensurate periods, and we can. This is a really irregular function. The previous one was a periodic function, the combination of two trigs. Now we get function which is not periodic. It's a sum of three periodic functions, but it's not periodic. But it probably never reaches the maximum value and minimum value is never really equal to min limit and max limit. But in the limit, that's what we get. So here's a larger plot of the same function. Oh, that was it. So Devendra will continue.
Thank you, Adam. So in the remaining time, I'll talk about discrete limits in brief, and then talk about documentation and benchmarking and how we have tried to see how good we are in this release. So for discrete limits, the question is, what's the motivation for having discrete limits? Well, the point is that many processes in nature are inherently discrete. So if you have a discrete process, then you definitely want to have a kind of discrete limit. So here's a nice animation created by Itai for seeing how the area of a circle gets approximated by the areas of polygons. And so clearly that's a discrete process. You want to use a discrete limit for it. But you go beyond that, go to number theory. Many things are discrete. You might sometimes have a continuous approximation, but number theory really is where discrete things take precedence. You go to signal processing. You have digital signal processing where things are discrete. And of course, many dynamical systems, let's say in the chaotic case, are defined discretely. So you don't need discrete limits all the time. And we have kind of been able to compute them, usually incorrectly in previous versions. So we really need this new layer of solvers for discrete limits. And so we've gone ahead and added discrete limit, discrete max limit, and discrete min limit, which are the discrete counterparts of limit, max limit, and min limit. So for example, over here, you have sine of n pi, that's just 0, and the solver knows that the n over there is just an integer. That makes life much more convenient for everyone. And of course, if you're doing college calculus, you definitely want to have a discrete limit. Sequence limits is chapter 11 or whatever of every textbook on calculus, 2 or whatever. We've done discrete calculus in the past for a long time. That requires discrete limits. So we definitely need these functions, and now they are there. Okay, so some examples of discrete limits which go a little beyond the continuous case. So one example over here would be periodic sequences, where you have something like a mod, and the sequence now oscillates, goes up and down from, in this case, it goes down from 1 to 5. So, of course, the limit doesn't exist. So, with the new philosophy, it's indeterminate, but surely we can compute the discrete max limit and the discrete min limit. So, that's 1 and 5 as expected. Okay, another example, the so-called densely aperiodic class. So, things like sine and cosine n are quite hard to work with in the discrete case. To prove that the limit of sine n goes to infinity, as n goes to infinity, the indeterminate is quite hard. But fortunately, we have the technology for doing this now. And so, if you look at the plot over here, it's wildly chaotic, goes between 1 and 2.2 roughly. So, the discrete limit does not exist. But using Adams' technology for max and min, we can simply forget the fact that n is discrete for a few minutes and get exactly the same answer that you would in the continuous case. So that's the idea of passing from discrete to continuous when required. And of course, in this example, the min limit is just 1. Now, we spent some time looking at number theory. That's a big area, but we have made a beginning. I would say this time we'll keep going in that direction. So for number theory, things like the prime number theorem, where you have an asymptotic estimate for, let's say, the primes, is now known to discrete limit, not to limit, because it's a discrete problem. And of course, you look at the partitions of an integer. Again, there are formulated Hardy and Ramanujan, which will give you a nice asymptotic. So those formulae are known, and they work quite well in tandem with other parts of the system. So discrete limits are really proving to be quite useful. But as a final example, here's a recursive sequence. That's the kind you'd see when you, let's say, study fixed point theory or chaos or something of that sort. So that's a nonlinear recurrence. And here's the first term. You want to find the limit at infinity. So that's a new convenient notation. Just say x of infinity, and you'll get back the fixed point essentially. So you get back a root object whose approximate value is 0.45. And you can then visualize the convergence of that sequence to its limit, and it's pretty fast. So what we've done was actually took all the 50 examples on MathStack Exchange, and we made sure they worked with our new functionality. And then within a few days of shipping 11.2, someone asked the same question on Mathematics Exchange, and I quickly replied. It's almost like I was waiting for that to happen, and it's nice when you do things which are really useful. So recursive sequence limits are actually quite an important advance for this particular area. Okay, so I'll now pull back and look at the whole limit functionality. So we have really worked hard. When I say we, it's really ITA in this case, who's worked very hard to make the reference page for limit, discrete, and etc. really modern and up to date. And so if you look at the limit page, it's completely redone. So there's some nice notes from Roger and an illustration from Tim, who's an expert in this area. There are lots of scope examples, many more than the 6 or 10 or whatever they were before. Lots of applications from our experience with college calculus benchmarking. So generally speaking, this is a complete introduction to limit in the system. So in discrete limit, etc., I've got ways to typeset things. So if you want information, the reference page is now the place to go. It's completely up to date as far as version 11.2 is concerned. So documentation is a very important advance for this release. And finally, we wanted to check how good we are. So I asked Michael Trott, can you give me some examples from Wolfram Alpha for the multivariate case? I thought he might give me a 50, 100, or 500 maybe. He sent me 100,000 examples in a package. And so we started testing them. And so when I say we, I mean Henry Kwong, who's an expert at benchmarking all kinds of things. So we ran the benchmark with the Wolfram Alpha limits and compared with Maple. That took some time, but it turns out that we actually do 91%, which is what Adam mentioned, and Maple does 76% of that benchmark, which is quite good proof that we have done a pretty complete job on the multivariate side. So meanwhile, I got brave and asked Michael, can you also give me some univariate examples? So he sent me 1 million of them. So we ran those, and this time we ran them with version 11.2, Maple, and SymPy, which is relatively new. Now, I believe SymPy doesn't have multivariate limits, so we only have univariate case comparison. But what happened over there was that version 11.2 gets 97% of them right. Maple gets 91% right, 93% right, sorry, and SymPy gets as far as 80%. So you have these huge gaps showing up when you do very large scale testing. And the reasons for difference are various, even things like conditional expression, indeterminates, are really proof the limit doesn't exist. And I think that these improvements are really proving to be crucial for our benchmarking and other purposes. So we have all these vast tests, and we thought we should share some of them with people outside. So we picked 1,000 multivariate examples, and sometime next week, I'm hoping to publish a blog post with some of the examples. That's 237 megabytes worth of multivariate limit examples, which we'll let people have a look at. These are really the most difficult examples, and Adam just finished looking at each of them individually this week to make sure that they are all fine. So we have been testing on a large scale. We've tried to do our best to look at textbooks, other sources, etc. And I really think that these benchmarks are now telling us that limit in version 11.2 is extremely powerful, well documented, well tested, ready for universal use. So it's very satisfying that it's all ended this way. Okay, I'll stop over here with a few remarks. So the main point, I guess, is that in version 11.2, you can explore the world of limits. You don't need to say univariate or function or sequence or whatever. You can do whatever kind of limit you want. It all works nicely. So we really have the world of limits opened out to us now. And to go further, we'd like to improve series, because that's where all the work gets done. We want to have a better series object which understands much more of the asymptotic philosophy which we are working on. And of course, we want to improve other functions, like we spoke about asymptotic desolve, etc. this morning. So together, we'll have a pretty complete set of asymptotic functionality in the next release or so. This is what is happening on this side, and thank you very much for listening. If you have any questions, I'll be happy to answer.